Yeah, here we go. Hopefully the audio is working. We'll find out when I replay this. Okay. No, I don't want to do that. All right, I was going to end the meeting. No, I think I'm up and running. All right, we'll find out. So here are a little bit of practice, getting the conversation started with new material for the second half of the semester. We're going to delve more deeply into some of the functions that we've been working with, look at them in greater detail, maybe even take a microscope out. All right, so first question was to sketch an absolute value function, and you've already done that. So I hope I'm not showing you anything different here. But to get from 17 to 7, you go down 10. To get from 0 to 5, you go up 5. So we have a constant rate of change of minus 2 to 1 on the left. To get from 7 to 17, you're going to go up 10. And to get from 5 to 10, you're going to go up 5. That appears to be going up at 2 to 1 on this side and minus 2 to 1 on that side. And I think there's two branches. Don't let these arrows fool you. Decreasing, then increasing. 17 goes to 7. Those numbers are going down. 7 to 17, they're going up, right? And the multipliers determine slope when something is to the first power. And that really is x minus 5 to the first power. All right, so the sign change that should happen at 5 doesn't happen because the absolute value kicks out the positives. Okay, so now we're going to write that as a piecewise function. All right, so let's get rid of this and write it as a piecewise function. And let's use a small graph over here. And I'm not going to put the arrows in. I think I'll just, we know that it continues on, right? But this is going down at 2 to 1. This is going up at 2 to 1. And we have a most important x value here, which is 5. And I'm not going to write the y value. I want you to really see this x value. So how could I put this in a computer and get the same graph? Well, if I was working with Desmos, right? Desmos has a little rectangle where you can write the equation and then another place to write another one. And if I wanted to get this graph in Desmos using pieces, then I would have to write -2, the downside, passing through the point 5, 7. I'm going to write x minus 5 plus 7. Looks like I got to have a little more space here. But that's only true until I get to what x value? 5. And this line is to the left of 5. So to let the machine know that, I've got to communicate it to the machine. Okay, so that's that branch, and it stops when x gets to 5. Okay, so that's all this would graph. This would graph all the way to 5, and then it would just stop. And then we want to have what? The other branch going up 2 to 1. But that only happens when we get bigger than 5. And at 5, we do get 7. So we've got to define that, and it doesn't matter which one you put or equal to. Okay, and that's writing this as a piecewise function. And now I'll erase that stuff that we don't need. Right, and we usually bring in a little bit of bracket of some kind, and then we say y equals. That's a piecewise function. You know, breaking this V shape up into 2 pieces, one the decreasing side, the other the increasing side, and I've defined it. Now we're going to solve this for 17. And I got my science card. This is so much fun. Love my little science card. My little teacup. No, that's some other song. All right, so f of x equals 17. Well, I got a new way of writing f of x over here. I'm going to write the pieces. The left-hand side, I want to know when it hits 17. And I want to know on the right side hits 17. And there's shortcuts to this process that we will uncover as we start our repetition. So you should be able to follow what I do. Subtract 7, divide by -2, add 5. 0 should work. Over here, subtract 7, divide by +2, add 5, 10. Well, I think that 0 and 10, let's get that graph up one more time real quick. So let's just look at it over here. X minus 5 plus 7, right? V shape. 5, 7. I wish I didn't have 0, but 0 gets me 10. 0 gets me what? 17. Well, that was actually my y-intercept. And 10 gets me 17. All right, so if I change by 5 units, I'm going up 10. So therefore, if I change by another 3 units, I should go up 6. So 13 should get me 23. Let's put 13 in just. Oh, well, that's 8. 2 times 8, 16. 16 and 7, 23. And it looks like it's positioned correctly. And you can check some points out on the other side. And I would say that 0 and 10 divided by 2 tells me that the most important value in this absolute value is 5. And, oh, I can see that clearly now. Well, I can see clearly that 5. That's a quick way to check that you haven't made a careless error. Now we want to know when we're greater than or equal to 17. Well, I know when we're equal to 17. We just found that. We just found that we're equal to 17. That's 0 and 10. Okay, so those numbers work. Well, there's only 3 other possibilities. Numbers could be bigger than 10. Let's find out. Most of you said 11. That's okay, we can do 11. We put 11 in, that gets me 12 plus 7, which is 19. Is 19 bigger than 17? True. True. Is it okay if I just write a T? True. I got a feeling this is going to be false and this is going to be true because I've seen the patterns. And I also know that linear functions have sign changes. Right? Linear functions tend to cross the x-axis from either negative to positive or vice versa. But there's going to be a sign change at the number 10. All right, so I don't know if I said that the way I wanted to, but let's check. Not a sign change so much as we're going to be less than or greater than, we're going to get a change. All right, so put a number in. We already did, so that's true. So now we're looking at maybe putting a 5 in. Oh, we already know what that is. That's 7, right? 5 gets you 7. And is that, what am I starting with here? Oh, greater than or equal to 17. Is 7 greater than or equal to 17? I don't think so. That's why I already knew. And if we put a number less than 0, I like 1,000,000. So let's put minus 1,000,000 in. And what happens to minus 1,000,000 when the absolute value of that? 2,000,007. Is that bigger than 17? I sure think it is. And we started to look at interval notation. So what did I want? Greater than or equal to. So negative infinity to 0, and 0 works. So bracket. Union also, what also works? 10 works. 10 gets me 17. And I can go to infinity, and we cannot bound infinity. Doesn't stop. Boy, that infinity is nasty. All right, in this process, this number line can come into play in so many different ways. If you learn to use it, you can solve a lot of things. Like, for instance, the domain of this problem. Here's a function, and we want to start getting a better sense of what domain is. I'm sure you heard it in Algebra 1. You're going to need to hear it more often if you don't know what it means. Let's see. Yep, that's where we are. So we have this function, a square root function, and a little division. And domain means, can I use a number? Can I use the number 10 in this problem? Can I use the number -3 in this problem? Can I put an infinity into this problem? And can I get a sense that it's a calculation that can be calculated? And so what are we going to do with it? Well, we're going to look at the critical numbers, which appear to be 7 and -2. And this breaks this up into 5 possibilities. Numbers less than -2, the number -2, numbers between -2 and 7, the actual number 7, and numbers bigger than 7. And we're going to try 5 different numbers, trial and error, to see if we can work with them. I always start with a number bigger than the number on the right. And we'll see why over the course of time. Generally speeds the calculations up based on is there a sign change or not. Keep that in mind, just putting a seed in your head here. All right, so put a number bigger than 7, 10. Can I do 7 minus 10 inside a square root? And will it show up somewhere on the Cartesian coordinate systems? And the answer is no. Right? The square root of -3, we write as the square root of 3. Imaginary. Imaginary numbers aren't on Rene Descartes' Cartesian coordinate system. So no. And instead of saying true or false, I'm going to write no, I cannot use no. Can I use the number 7? If I plug 7 in there, I get the square root of 0 over 9. Will the calculator kick out that answer? The answer is yes. The square root of 0 is 0, and 0 divided by 9 is 0. You put it in the calculator, it works. Understanding the square root of 0 is understanding the square root is the length of a square, and I can keep making that smaller and smaller and smaller until it's 0. Can't draw it, but 0 times 0 equals 0, so it's a square root. 0 times 0 gets me 0. All right, so no. Oh yes, this is a yes. I can use this number, I'll circle it and go yes. Can I use numbers between -2 and 7? I hope you pick 0. Let's put 0 in here. If I put 0 in for x, I get the square root of 7 divided by 2. I don't think there's any problem with that. Square root of 7 exists. That length exists. I can cut it in half. And that length exists. Okay, so yes. Well, what did I say? Yes, yes, these numbers work. How about -2? Well, I put -2 and I get the square root of 9 over 0, which is equal to 3 divided by 0. And I'm sorry, folks, but that does not work. Null set. Yeah, and that came about in 1877 in Mrs. Johnson's class, where a student said, oh, 5 divided by 0 equals 0. And the teacher went, Johnny, no. She put a slash through the 0 and created the null set. Yep. Anybody believe that? I got some land around the corner, sell you. All right, so that takes, oops. So that one did work. How about numbers less than -2, like -3? Let's subtract a -3. That gives me the square root of 10 in the numerator. Let's put -3 plus 2, that gives me minus. Will there be a number, the -√10? I think so. It might be approximately what? -3.1-ish, something like that. I'm guessing. So what do we have? We have a yes here. We have a no here. And now we're going to write this in interval notation. So what do I see? I see -infinity, which cannot be bounded, to -2, which does not work. What does work? -2, which doesn't work, to 7, which does, bracket, and no. So that's it. There's your answer. Try to learn interval notation. So let's make a little space here. And why am I asking this question? Because we're going to do the same thing. We're going to do the same thing. And these questions can probably be done in 20 seconds or less once you see the patterns. For right now, we've tried to learn, what are the answers to this? It's been on every test since the start of the term. And I think most everybody's got that down, I hope. So what are the critical numbers? 0. Watch, I'm either going to do a dash or a dot. Try to explain why. 0, dash. 2, dash. -4, dot. +5, dash. Right? Obviously, it has something to do with whether the exponents are even or odd. And sign changes, because this is a product. What's a positive times a positive times a positive? Yeah, that's greater than 0. But what happens if one of them changes signs and the other doesn't? Well, it's not true anymore. And that's what we're going to be looking at. X to the 1, linear function, changes signs. X minus 2 goes through 2, 0, changes signs. X plus 4 squared. No, the y values are always positive, except for that one minimum. X minus 5 cubed. It'll look something like that. It changes signs from negative to positive. So we get sign changes with odd exponents, and we don't with even. That's what you're going to be looking at. All right, so what do I see? I'm going to see a number bigger than 5. I'm going to go true or false. A million cubed times a million squared times a million minus 2 times a million. Yeah, that's definitely bigger than 5. And I know the next one's going to be false because there's going to be a sign change. If I put the number 4 in, when I put the number 6 in, this is positive. When I put a 4 in, it's negative. When I put the number 6 in, that's positive. When I put the number 6 in, that's positive. When I put the number 6 in, that's positive. When I put the number 4 in, that's negative. 4 plus 4 squared, positive. 4 minus 2, positive. 4, positive. These terms did not get affected. But a number bigger than 5, positive, a number less than 5, negative. So there's a sign change, which means positive is greater than 0, but 1 negative on the multiplication, less than 0, false. I'm going to get a sign change of 2, so that's going to be true, that's going to be false, that's going to be false. And I know that from the odd and even exponents. You're going to have to hear that for 3 or 4 days and practice it again for a week or 2 until you get some facility with it. This is just getting the conversation started, putting the thoughts in your head, those thoughts that you need to consider. All right, so let's try. I'm at 2. Next time I write these, I'll write them in ascending order. Might be a little easier for you. But what's going to happen when I put a number less? This 4 is bigger than 2, so I've already done that. What's less than 2? Let's put 1 in here. Doesn't affect this one. That's still positive. But 1 gives me a sign change. 1 doesn't affect this, and 1 doesn't affect that. But I do get 1 sign change, which means the product goes from less than 0 to greater than 0. And I'm going to get a sign change at negative 2. Let's put negative 2 in. Negative 2, ooh, there's my sign change. Yeah, because this is really x minus 0. Right? We've already checked 2 out, now we're checking negative 2. Minus a minus is still a minus. Anything squared is still positive. This is not changing. And minus 2 minus 5 cubed is 3 negatives, which is still negative. I get 1 sign change, which means I go from false, from true to false. Okay? And now a number to this side of negative 4. The only thing negative 4 is affecting is this parenthesis. But because it's squared, it's still going to be positive. All right, you put negative 8 in. Right, you square it, you get a positive. You put negative 8 minus 5 in cube, it's still negative. Well, you better put the negative there. You put negative 8 here, minus 8 minus 2, still negative. But you put negative 8 in here and it's still negative. So I think I got no sign change, right? No sign change there, no sign change there, no sign change there, no sign change there. If it was false here, it's still false there. All right, now, the other thing we're going to learn to do is to graph this. And what I have here at 5 is a cubic. It's bigger than 0. Polynomials, just look at the end behavior of the square. Go up, but this is a cubic, and I'll explain why more later. A cubic root, a linear root at negative 2. We'll throw some numbers in here at some point, but not right now. A linear root at 0, and a quadratic root at negative 2. That's what the graph looks like. Where am I bigger than 0? I hope you can see these y values are above the x-axis, and these are above the x-axis. So in interval notation, when are we greater than 0? 0 to 2, and 5 to infinity. That took a while to do that problem. If I wanted greater than or equal to, then this parentheses becomes a bracket. And being able to graph these quickly and easily comes into play in a calculus class in a big way. All right, and the calculus teacher doesn't want to have to teach you how to do this. So that's why we're learning it now. Okay, 3 more problems. And it's taking a little longer right now because I've got to give some initial explanations. All right, but we want to look at when is this less than or equal to 0, and I hope you're getting the hang of a number line. All right, so I'm just going to say true or false, -9, and I know there's a sign change. 3x minus 12, 4 is the critical number, and I know there's a sign change. If I put a number like 1,000,000 in, 1,000,000, 3,000,000 over 1,000,000 is what we basically get out of that fraction. That's a positive number, no, false. So it's going to be true, it's going to be false. You can check it with some numbers. Put a 0 in, 0 is really easy. X's cancel, you get minus 12/9. Is that less than or equal to 0? Absolutely. Okay, put a 4 in, 4 over 13. True or false? Does that equal 0? Or is it less? Excuse me. 4 gets me 0 over 13. Is that either equal to 0 or less than or equal to 0? Yeah, it's equal to 0. So 4 works. Does -9? No, -9 puts a 0. We talked about that in the previous problem. Doesn't matter what the number is. Can't divide by 0, so I'll put a slash there. Can't use that number. All right? And I know that it's not going to work for -1,000,000 because a -3,000,000 over -1,000,000 becomes a positive number. And so it doesn't work. So interval notation, -9 doesn't work, 4 does work. I guess that gets the job done for x values. Nicer way to write that, but good enough for now. So keep that in mind about the positives and the negatives when we graph this. And I think these will take you a couple of weeks of practice. If we can get to do 1 or 2 every day for a couple of weeks, I think we'll start to get the hang of these. All right, but these are fractions, and fractions can be big. They can be small. They can be positive, they can be negative, they can be 0, and they can be undefined. So we got everything coming at us in these graphs. So what are the critical numbers? Well, certainly 4 makes it 0. When the numerator of a fraction is 0, the fraction is 0. -9, not drawing a scale here. All right, I'm not going to draw, let's put the 4 there. 4 is 0 there. That way it just looks a little bit more size appropriate. X equals -9. Can't use -9. Graphing computer is going to look for an answer, not going to find one. -12/9, which is minus what? Put a 3 in each, 4/3. -4/3, right there. 0 gets me -4/3. I know this thing goes to a height of 3 on both ends. You may be wondering why. And I know there are no other x-intercepts other than that one. Right, that one, 4 gets me 0. There's no other way to make this fraction 0, just the numerator. Man, you're going to have to hear that every day. And I know the bigger the number, the closer this gets to 3x divided by x. If you put a billion in there, I don't think we care about, if you're a billionaire and you lose $9, you should care. You should care, but you probably don't. All right, so it's a ratio that as we put big numbers in, I'm actually looking at numbers that are basically, well, I don't want to say unless I say something that I'm sure of. I was going to say it, they're about 21 apart. About. All right, so what happens at -9? Well, it's what happens is when I get to -8.999 plus 9, there's a numerical look. That's like dividing by 0.001 into some number. It's going to go lots of positive times. No, I don't want that. I want a negative. So what did I do wrong? Oh, I forgot to put it in here too, because that's a negative, right? It's going to go lots of negative times, which means -8.99 is here. Lots of negative times. Move this to the side. Right? If I said that better, it's heading to -infinity. Right? And yet if I put a million in, I'm really looking at the function 3,000,000 minus 12. That's 6 zeros. Divided by 1 million, 6 zeros, plus 9. Honestly, these numbers at the end don't matter. This is really about 3 million divided by 1 million, which is roughly y equals 3. And if I don't have any other x-intercepts, and if this is the first time you're watching this, your head's probably spinning, let it spin. I know there are no x-intercepts over here, and I know I'm ending up in the same situation over here, because if I make these negatives, I'm still heading to 3. And then what happens when I put in not negative 8 point, but negative 9.1 plus 9? I get a sign change, negative point, well, I don't know. And that's going to fit into something close to negative 27 minus 12, negative 39. Negative 39, and I'll just highlight it. You tell me what you get. Phew. You get a 0, a 0, a 0, a 0, a 0, and a 1. God almighty, that's an awfully big negative. But it's also divided by a negative, which makes it an awfully big positive. All right, kind of lost. That's okay. We've got our first rational function there called. And then there are a couple of questions about really what I've already talked about. So limit of g of x as x goes to negative 9 really means from the positive side, I'm going to negative infinity, and g of x to infinity is going to 3. So I really already talked to those. And I got a phone call coming in, so I'm in the meeting and answering it. Bye.